Now that we've looked in some detail at what happens to that matrix in the normal equations, let's recap the whole process and talk about its efficiency as well. So remember that we solve the least squares minimization problem if we solve the normal equations that go along with it. So the first step in this process would be to form the matrix S here as A transpose A. Now let's talk about the efficiency of that. It's just a matrix multiplication. So in general, if I have matrices B and C, and one of them is m by n and the other is n by p, okay, multiplying them together takes asymptotically 2 times m n p flops. Oops. And that's just because in each element of the product there's an inner product of two vectors of length n, essentially. So that's the general case. Now in this case we know that S is symmetric. So the entries in the upper triangle are just copies of entries in the lower triangle. So we only have to compute, roughly speaking, half the entries of the matrix. And if you do the analysis in detail, that proves out to be true. Remember, A is n by m, or I'm sorry, A transpose is n by m, A is m by n, and so what we get is m n squared flops using the symmetry. Okay, once we found S, we can find its Cholesky factorization, which we said takes 1/3 n cubed flops. Then we form the vector A transpose times B, so that's an n by m matrix times an m by 1 vector, so that's on the order of 2mn flops. Then we do back substitution of size n by n, that's on the order of n squared, and the first one was a forward substitution, that's one's a back substitution, that's n squared flops. So all those things are insignificant compared to the two things that have cubic properties, right? All the other terms are insignificant next to these dominant ones. Now, unless we know something about the relationship between m and n, we don't really know how to balance these two terms. So we just add them together. So what we say is that the total algorithm takes mn squared plus 1/3 n cubed flops asymptotically.